Here in these notes, we are going to talk about ordinary differential equations. Okay, let's start with the definition. An ODE, an ordinary differential equation, is an equation that involves an unknown function, u, and we call it ordinary because we only have one variable involved. Differential because the equation involves the derivatives of this function, u. So in this course, we will focus only in linear ordinary differential equations, and those have this form. We have this unknown function u and some derivatives of this function. The first derivative, the second, let's say here we have until the nth derivative of the function u. Then we have other functions involved that they have a name. They are called coefficients, and those are these functions a0, a1, a2, and so on until this an minus 1. So those are called the coefficients of the equation. We only will see here linear ODEs. And we also have this function g that sometimes is called the driving term. When this function g is 0, we call the equation homogeneous. And when it's not 0, then we call it non-homogeneous. Okay, maybe it's a bit trivial, but we have to say it. A function u is a solution of this equation with a star if we can differentiate the function n times and the function u verifies this equation. Okay, so we can classify the ordinary differential equations, let's say like people, when we can, I don't know, classify people in groups regarding the age. Let's say here there is a group with 20 years old, then another group with 30 years old, and so on and so on. Okay, so we can also classify an ODE within this class of linear ODEs. So how do we classify them? We can look at the order of the equation, which is the highest order of derivative that appears. So here, if we look in this equation, the order is n. Then, as I already said, if this function g is equal to 0, we call the equation homogeneous, and otherwise non-homogeneous. Okay, so basically we have these two features to classify these linear ODEs. Example. We have here a function u that we don't know. Here is u, and here is the third derivative of u. And this is our coefficient h0 that we can see here, next to u. Okay, sorry. And this is our function g, x squared. Okay, so this is a linear ODE. Yes, we already checked that we have some derivative of the function that we don't know, u, this coefficient, and this function g. And which is the order of this equation? Well, okay, if we look at this, we know that the highest order is 3, so 3. And it's not homogeneous because our function g is not identically 0. Okay, so here we have, this is a third order linear non-homogeneous ODE. Okay, example 2. Let's say example, but this is not a linear ODE. And we can see here the red part. We are multiplying u, but its second derivative, and this doesn't fit in the definition of being a linear ODE. But don't worry about this type of equations because we won't see them in this course. Okay, so some basic questions that maybe we address during the course is, okay, I see an ordinary differential equation, and I wonder if I can find solutions. So existence of solution is something that we want to talk, to learn. Then imagine that I find one solution of the equation. Is this solution unique? So uniqueness will be also something that we sometimes we want to check. And imagine if the solution is not unique, I have more than one solution. How those solutions are related? Are they independent, linearly independent in some sense? Or what can we say about those solutions? And of course, how to get those solutions, how to solve an ODE. So we will try to answer totally or partially these questions for some specific class of equations. So now in this note, we are only talking about linear ODEs. Okay. So here we have again the general equation with the function u that we don't know, these coefficients a0, a1, and so on. But we start with the homogeneous case, which is when this function g is equal to 0. And now we try to say something about this special case, which is maybe the easiest. We have a nice property for this type of equations, which is, okay, imagine that I have two solutions, u and b. Since this equation is linear, then when I take any linear combination of these two solutions, I get a new solution, a third one. So this is because this equation is homogeneous, and of course because it's linear. You can check that. It's a nice exercise if you want to do that. Okay, but now imagine that I have these two solutions, u and b, sorry. Now I know that this is a new solution, any combination. Let's say 5 times u plus 6 times b. But someone says like, hey, w is also a solution. Okay, so then this new solution, let's say 5u plus 6b is one solution, w is one solution, so any combination between this new solution plus w is again another solution. So what I'm trying to say is that if I have if I know certain amount of solution, u1, u2, u3, and so on, then since the equation is linear and homogeneous, I can take any linear combinations of those solutions and I still get a new solution. Okay, this is written here, then you can read it, but this has a name. We sometimes won't care about the name, but it's good to know. It's the superposition principle. Okay, so this is just what I said. I have a couple of solutions, u, b, and w, then the combination is again, any linear combination is again a solution. And the conclusion in general, if I have k solution, u1, u2, uk, any linear combination is also a solution. Okay, so looking at this equation, so far we only know that if I have some solutions, u1, u2, etc., then the linear combination is a solution. Any linear combination is a solution. But we don't know how. We don't know yet how many solutions do we expect of this for this equation. How many essential solutions we have. We will talk about this in a few minutes. And okay, what do we mean with essential? Let's check this idea. Imagine that I have an equation, a linear homogeneous equation, and I realize that 5 EX and 8 EX are solutions of this equation. But those functions are practically the same, right? If 5 times EX is a solution and 8 times EX is a solution, we would like to say that, okay, essentially I'm talking about this function, EX, and well, the number is around. This is just an idea, it's not rigorous, so don't take it for true, but this is just an idea. We don't want to count solutions that are quite similar, let's say. Okay, so to try to understand what do we mean with how many solutions and how many essential solutions, that maybe a better word is fundamental solutions, but just in 1 minute we will check that. We introduce a concept of linear independence of a set that maybe you are already familiar, but let's recall it. Okay, I have this capital U1, capital U2, capital UN, n vector functions. Well, here is the formal definition, but we are not going to read that. And we take this set, the set of the functions U1, U2, UN, capital U's, and we said that this set is linearly independent if I take these combinations. I take this combination C1 capital U1 plus C2, this combination here, equal to 0, 0 in Rn. Oops. So we are here, sorry. If we have this identity, this linear combination, where this C1, C2, and Cn are real numbers, then the unique solution of this is that all these constants are equal to 0. Okay, this is the concept, the definition of linear as this set being linearly independent. How do we use this in the context of ODEs? So let's get back to our linear homogeneous equation with this purple triangle. So let's go there. Where is it? Here. Okay, so we have this equation, which is an n, the order is n, and is homogeneous. So we wonder, this number n is related to the amount of solutions that we have, the linearly independent solutions. Well, the answer is yes. We are not going to give the proof here, but there is a fact. We have these coefficients, the coefficients of the equation, and if these coefficients are continuous functions, then we know that our equation has n solutions, u1, u2, un, such that this set with vector functions is linearly independent. So which are these functions? Capital U, capital U1, capital U2, capital UN. So those vectors are here. For the first one, we take the first solution, its first derivative, its second derivative, so on, so on, so on, until the n-1 derivative. And we do that for each of the solutions that we have. So we are here again. Okay, so we have this, we know that we have these n solutions, u1, u2, un. what we do is build, in some sense, these vectors with the derivatives. So I collect in capital U1 all the information about U1, the function U1, the first derivative, the second one, so on, until the n minus 1. I collect in U2, in the vector capital U2, all the information about U2. And with all the information about U2, I mean the function, the first derivative, the second derivative, so on, until the n minus 1. And we do that for all the solutions. Okay. So what I'm trying to say is that when we have this linear homogeneous equation with order n, and we find n solutions, we know that there are n solutions that such that this set is linearly independent. And any solution of the equation is a unique linear combination of those n solutions. Okay. So this set of solutions has a name, is the fundamental set of solutions. That I don't remember if you remember that I was using the word essential before. How many essential solutions this equation has? Well, okay, maybe the essential wasn't the right word because we are using fundamental set of solutions. Okay. And any linear combination of these n solutions, we call that the general solution of the equation, the linear homogeneous equation. Okay, let's see an example trying to fix these ideas that we just saw. Okay, here we have second derivative of u minus u equal to 0. Is a linear ODE, is homogeneous, we are okay. And the order is 2, second order. Okay. We will see later how to find solutions, but let's now just believe that we have these two solutions, ex and e minus x, are solution of these equations. Then we wonder if this set is a fundamental set of solutions. So what do we have to check for really proving this? So first observe that we have a second order linear ODE and we already have two solutions. So we are in this situation, right? Let's go to this fact. We have some equation and we have n solutions. In our case, we have two solutions, u1 and u2. So to prove that these solutions are a fundamental set of solutions, we need to check that the set capital U1, capital U2 is linearly independent. And here we have how to build these vector functions. Okay, so that's what we are going to do. So going back to the example, someone says that these and these are solutions and we can verify that. So we already have, for our second order ODE, two solutions. Here we call U1 this one, EX, and U2 EX minus, E minus X. And now we want to prove that this capital U1, capital U2, this set is linearly independent. So here we have the vectors function. The capital U1 has all the information about U1, meaning U1 and its first derivative in this case. Our equation is order 2, so we save the information until one less derivative, let's say. And okay, EX is super easy function to derive, so it's EX. For U2, capital U2, we have all the information about little u2, which is just u2 and its first derivative. And here we have the derivative of e minus x is minus e minus x, chain rule. Okay, so we need to show that the unique solution of this linear combination equal to 0 is the constants C1, C2 equal to 0. Okay, so we write who these vectors are here. Then we rewrite this side of the equation as a matrix times these vectors C1, C2. And now some easy thing to do is to check that this matrix has determinant different to 0. Because in that case, we can invert this matrix, and that means that the unique solution is the vector C1, C2 equal to 0. And that's what we are going to do. So, calculating this determinant, remember that is this one times this one minus this one times this one. So doing that computation, we get this number minus 2, which is not equal to 0. Then the unique solution is what we want, the constants equal to 0. So this set capital U1, capital U2 is linearly independent, and that means that our set of little u1, little u2, ex, e minus x, is a fundamental set of solution for our second order linear equation, homogeneous equation. And moreover, we can say that the general solution is any linear combination of those functions. Okay, maybe some remark. This C1 and C2 have nothing to do with the previous C1, C2, so maybe we can just put some other names so it's not confusing. They are not relating to, let's put like A and B in R. Okay. But hopefully this is clear. Let's continue now with non-linear, non-homogeneous ODEs. Okay. We have